Morning AP Calc kids. Today you're listening to Math Sounds with Sindoni. Today's episode is brought to you by this brand new spike ball that I found in my room. Spike ball. Put it right there. Alright, today I'm going to do the 1.4 lesson. And then later on today I'll do 1.5 and assign a few problems for those sections that we'll go over on Monday. I won't be posting anything Thursday or Friday, so I'm just going to post both assignments today, and you can take your time and spread that out over the next few days and or weekend. Okay, so let's take a look at 1.4. Let me move this a little. No. Alright, that's fine. There we go. That's a little better. Okay, we're going to look at continuity and one-sided limits. I will be putting the book up to the camera at the end of the video so you can look at the pages, pause the video if you want to read through the section, and then at the end you'll see the problems you'll be able to do them from. Let's get started here. If a function is continuous, aka no interruptions, the following must be true. In the past, you've always been taught that if something is continuous, that means you can draw it without lifting your pencil. That is an informal definition, of course. Now that we understand limits, I can give you the real definition of continuous. Condition number 1. F at C, we're going to say if a function is continuous at C, F at C is defined. What does that mean? Well, I'll give you a counter example. If you have a function and it's just chugging along and then there's a hole here, that is bad, okay? Not this. Okay, it must be defined wherever you're looking at. Condition number 2, the limit must exist. The limit, as x approaches whatever value you're looking at, exists. Alright, and what does this mean? Again, I'll give you a counterexample. If you're chugging along and whoop, there's a gap. Then you keep going. Okay, that's not this. And the third condition, the limit as x approaches C of f of x is actually the value if you plug in C. Okay, for example, here's a counterexample. You're chugging along, you got a gap, and it's defined somewhere other than where it's supposed to be, where the limit is approaching. Focus. There we go. Alright, not this. Alright, so those 3 conditions must be met in order for a function to be continuous. Okay. Come on. Sorry. Okay. Moving on, we have a couple little notes for you to have down here. F is continuous on an open interval A, B. continuous at every point in the interval. Alright. Functions are called continuous everywhere. Oops, everywhere continuous. Whoopsies. Everywhere continuous. If continuous, I'm just going to abbreviate on the interval negative infinity to infinity, of course. Alright, so we talk about removable discontinuity. Okay, this is if you have something like this right there, and you can fill that with with something else, you can define that as a function that's removable. Non-removable would be like asymptotes like that, where it's impossible for you to fill it and keep it continuous. Whereas this one, you can fill that by having something else like a piecewise. Here you cannot. Okay. Let's talk about one-sided limits. These are limits where you are only approaching from the left or the right. Here's your notation. The limit as x approaches c. The plus sign to the right is for the right. Okay. Limit from right. And the negative sign here, limit from left. This always got me confused when I was younger. Negative sign is on the wrong side, obviously, but if it's on this side, that means it's coming from the left, approaching from the left. Okay? Alright. In order, or is this the next thing? Alright, so in order for the limit to exist, which we've already kind of talked about, existence of a limit, if the limit as x approaches c from the right must equal the limit as x approaches c from the left. Alright, and we talked about that before. Both the functions have to approach the same number in order for there to be an existence of a limit. However, we can use these for interval functions. Alright. Let's do some more theorems. You'll see in your book. Actually, let me give you an example of this right here. No, we'll do that a little later. Yeah, we'll do that later. Okay. Existence of a limit. We did that. Properties of continuity. Properties. Continuity. Okay, this is theorem 111 in your book. If b is a real number, f and g are continuous. C. So all these are also continuous. B times f of x, f of x plus or minus g of x, f of x times g of x, and f of x divided by g of x, of course, where g of c does not equal 0. Alright, which is just kind of what we've been talking about before. You can add functions together, multiply, divide, and the continuity stays the same, the limit stays the same kind of thing. Multiply by a scalar. That was what b was for. Same is also true with a composite function with fog. This is theorem, this is, we'll say, composite function. This is theorem 1.12. If G is continuous, I'm just going to write cont, it's a lot, at C, and F is continuous at G of C, then of course that the composition is also continuous at C. Goody. Alright. Last theorem, theorem 1.13, intermediate value theorem. Intermediate value theorem. This is if f is everywhere continuous. Alright, if f a is less than 0, f b is greater than 0, then there exists at least one value of c in the interval a to b such that f of c equals 0. Okay, what does that mean? That means if you have some function and, you know, let's say a is over here, b is over here. If you have some function that starts for here in less than 0 and ends up over here greater than 0, it has to hit the x-axis somewhere in between that interval. Okay, it seems like common sense, but that's what this theorem states. All right. Okay. I'm going to show you the book pages now. I should zoom out a little. There we go. Okay, you may feel free to read this if you want to. Kind of look at some of the things we talked about and some of their examples. Example 1 is a good one, discussing the continuity. We didn't really go over this one. That's okay though. There's theorem 111. That's not blood, it's marker. There's intermediate value theorem. Alright, now here's the exercises. Should play some music. think I signed any of these. No, I don't think I did. Okay, look for 1-5 later on today.